Alrighty, guys. So, I wanted to do Zoom, just because I think it's a little easier sometimes to meet from the room. And to prepare you for your quiz tomorrow, basically all that's going to be on it is a bunch of reactions, which we'll go over every single one you need to know. And then the lipid stuff from the lecture yesterday, which is a lot more free form, just kind of general knowledge. So I have all of these reactions up and we'll go through each and every one of them. And I don't think I can see people. It's kind of weird. My screen sharing isn't allowing me to see people. So if you have a question, I'm going to stop after every reaction and be like, do you have any questions? And you can just speak up. Perfectly fine. You don't have to raise your hand or anything. Okay. So for the first reaction, it's an acid-base reaction. This is our acid. This is our base. So the acid is going to give up the hydrogen. It's a negative charge. And then the base is going to gain an extra hydrogen. So again, this is a review from the stuff from the quiz before, but she could still include this. Do you guys have any questions about these? Okay. So this one's very similar. It's another acid-base reaction. This is the base. And so we're still going to have this form, and then water. And then don't forget the sodium attached to there. So this one has 3 parts to remember because this ionizes in the water. Any questions about this one? Okay. So this next reaction, you have a carboxylic acid and an alcohol. And when you pair it with acid, you're going to be making an ester. So this is a salt. And so basically what's going to happen is you're going to replace the OH with whatever this is, then plus water. Now remember, this reaction can only take place in acid. So if she does not have acid on there, you would just write no reaction. You need the acid to catalyze the reaction because the alcohol and the carboxylic acid are both acidic. So they need something stronger to power the reaction along. Do you guys have any questions about that? Okay. This next reaction will be creating an amide. So this right here is an amine. And so very similar to this, to the one before, we're going to be dropping that H. And we're going to have now an amide. And we're going to have water. And in this one, you need heat. Any reaction or any questions about these first 4 reactions? Again, these are a review, but necessary review for what we're about to go over. All right. Ah, not it switching tabs on me. Give me a second. There we go. So we're going to do another page. Perfect. Can you guys see that? Okay. Somebody just say yes.
Yeah.
Okay, perfect. Thank you. So we're going to review another reaction. We're going to have an ethyl on this. I don't know why I wrote it so big. Oh my Lord. Okay. So this is an amine, which is a base. And then this is hydrochloric acid. So clearly an acid. And so when this happens, you are going to make another acid. This is an ammonium ion, NH3+. And then you'll have the the chlorine base. And so basically all that's happening here is that the base is gaining an extra hydrogen. It could look like this. Or it could look like if it has 3 carbons attached to it. Like this. Any questions about this one? This is just another acid-base reaction. So it's different from the past one that had an amine, is that this one is just an acid. This is not a carboxylic acid. All right. So we'll do one with a carboxylic acid. Oops. I'm gonna go back. This is heat. Right. So this reaction right here, we have a carboxylic acid, and then we have an amine. If you remember from the reactions we just did, if there's heat, it will make an amide and water. But if there is no heat, then it is an acid-base reaction in which you have this negative O here. And then you have this ammonium ion here. Oh, geez, that was terrible. Ammonia. So when you have heat, it makes an amide. When you don't, it's just an acid-base reaction. Does anyone have any questions about that? All right. And so just to review, I'm going to throw another one up here. We'll do HOME. So if you remember, if you add these two together, you make an ester in water. But if you add a bunch of water, you can reverse it. And so with this one up here, it's important to remember that if you add heat and this becomes an amide, then you can use water and acid to reverse it. Now, the one on the bottom is an acid-base reaction. It's not a substitution reaction where you're reverting one thing for another. Acid-base is a complete swapping of hydrogens. This is a swapping of groups. So it's very similar to our hemiacetals, right? Where you could go back because you're reversing that substitution. You're not reversing a hydrogen moving. So if she asks you how to reverse either of these two, this one is just water because there's already acid here. This one is acid and water. Does anyone have any questions about that? Okay. So there's an important few steps to this. And we're going to start again. We'll just do something simple. So with this right here, the amide is now the acid. And this is now the base, but they're going to be doing a substitution reaction. I'm going to scratch out this line right here. Ignore that. Plus NH3. So we're reversing this reaction of having this amide here. We're making it into an acid. And then we have this base here. Now, if you remember, this is going to be important. She's going to ask you about this on your quizzes. This is an important second step. But if you have something in acid, the amide and the water in acid, this base will react again. And that is a hydrogen. I apologize for how that looks. But this is going to react again and form an ammonium ion. Does anyone have any questions about this? So this one is the acid. You also have to know what happens when it's a base. So with the base, it's going to be a little bit different. We're going to do something that's not nitrogen because nitrogen is usually a base. So instead of acid, we're using a base here. This is going to pop off and be a negative. And then you're going to have your carboxylic acid. But remember, this carboxylic acid is still an acid. So now that this is a base, right, now that this is a base, this is going to react again. And it's going to form this. So the two important things to remember out of this is that if it is an acid, it will continue reacting. If it is a base, it will continue reacting. Does anyone have any questions about those two? And again, it's okay if you do. If we need to do if we need to do another example, we can also do that.
Yeah, can you do another example, please?
Yeah. I'm gonna start with this one. Oh my gosh. Okay. So it's gonna only be when you have an ester or an amide. So up here, it's a substitution. You're reverting the ester back into the carboxylic acid. This is popping off. And see how I just had like this random group attached to it? It's kind of to show that it could be anything there. So since this is an acid, it's going to react again. This is going to take that hydrogen off. So that's for a base. This here is an amide. This is water. This is an acid. So again, we're reverting it back to the carboxylic acid. So it's the same first step as the last time, reverting it back to a carboxylic acid. And then I have my N. That looks like this. It gained an H because it's in an acid. This is still a base. So this is going to react again. And that nitrogen is going to gain a hydrogen and become an ammonium ion. So it's all about following the same pattern. pretty much over and over again. And we'll go over, I'm gonna do some more examples where it goes the other way. So I'm actually, what I'm gonna do, I don't know if I can erase, so I'm just gonna go all the way back on this. And this is in a mid. I'm gonna cross this out and I'm gonna actually make it a base. So again, it's the same first step. This is the first step. But this right here is the base, so it's not gonna react again. This will. So do you see how it can go both ways? It can be both. And do you guys have any questions about that? If I were to do it with this one, right? It'd go to the acid, and then it'd have the HOET. I actually don't even think you need an acid for this one. Yes, you do. But in this case, right, usually if we think about it, you would keep reacting. But this is an acid. And this is an acid. They can't keep reacting. So this one is a case where the reaction stops. Do you guys have any questions about those reactions? If not, I'm going to move on to lipids. So the lipids that she talked about that you need to know are fatty acids, waxes, and triacylglycerols. So basically, she just gave you a bunch of information to know for the quiz. So a fatty acid, it's a carboxylic acid with a bunch of carbons off the end. And this is usually 12 plus carbons. And she introduced the terms hydrophobic and hydrophilic. And we can think about this with polarity, right? And how it would interact with water. So if we think about this, which one dissolves better in water? It would be this one. It would be the alcohol, because there's that area of polarity. So this area right here loves water. And she used the term hydrophilic. Now over here, it's basically this. And it does not interact well with water. So it does not like water. It is hydrophobic. And so that is the key characteristic of all of the lipids. It is that they are hydrophobic in water. It means they don't like water. So if you've ever put like olive oil and water together, they don't mix. If you clean your pan after cooking and there's cooking oil on it, it like saturates itself in the water. It doesn't mix with the water. So that's basically what we're learning about here. And again, for the fatty acids, there is not really a specific one you need to know. You just need to know the structure of them. So what she would say on the quiz is draw a fatty acid, and you would draw something like this. It could be very generic. Just make sure it has 12 carbons. So this is a squiggle, meaning that could be a billion carbons. So this one right here, she introduces the term saturated. So saturated is when it's a long carbon chain with all single bonds. Single bonds. When it is unsaturated, it can have double bonds. I'm going to go back and redraw this one because they're usually cis. So saturated, if you remember, when things do not have double bonds, they have the highest amount of hydrogens possible. It's the 2n+2. So saturated, if you've ever made lemonade, if you saturate the lemonade mix in the water, it tastes like powder. It doesn't taste like lemonade. So it's like this. Saturated means there's so much powder, there's so much hydrogen that there's no double bonds. Unsaturated is when there's not enough powder to how much water there is, just like how many hydrogens there should be, but there isn't as many because of the double bonds. And so when bonds are unsaturated, that lowers the boiling point and that lowers the melting point because the particles are not as compact together. So naturally occurring fatty acids, just a note, are currently have an even number of hydrogens. Or not hydrogens, carbons. They typically have an even number of carbons. Does anybody have any questions about fatty acids?
Where you said saturated has an even amount of carbons.
Either, does not matter. Any type of fatty acid.
So would unsaturated have a higher boiling point because of the double bonds?
No. So the double bonds, it actually, so how they interact in solution, there's not as many dispersion forces. And so less dispersion forces, because see how these cis double bonds wouldn't sit well against each other, but like a
Mhm.
spaghetti would. This would have the higher boiling point and the higher melting point. And we'll also get with that point with the triacyl glycerol. So we'll talk about this again. But typically the rule of thumb is that if there's double bonds and triple bonds in these like big complex molecules, that actually can make the boiling point and melting point less. The energy to break the double bond is higher though. But we're talking about intermolecular forces, not bonds between atoms. Any other questions about this? That was a good question. Okay. So the next one is super easy. So I'm just going to include it on the same page, and that's waxes. She will ask you to draw a wax, and this is all you have to draw. She mentioned in the video about beeswax. And so the left side of the carbonyl group has 15 carbons, and then the right side has 20 carbons. So I would possibly remember that maybe for the test or something, but for the most part, all you need to know about waxes is their structure and that they look like this. So this is an ester, and this is an acid. Does anyone have any questions about these?
Quick question. Was that a double bonded oxygen on a carbon and oxygen?
Let me find it. I think it was, or was it? Was it this one? So
For
it's
the wax.
this right here.
Yeah.
So it's a C, double bonded oxygen. This is a C, this one.
Okay.
It looks like an O, but it's a C. So it's literally if you wanted to draw it like this, you could draw it like this. I just choose to write the C in. Any other questions? So the last group, I'm also writing with my finger, so that's why my handwriting is terrible, so I apologize. But triacylglycerols are another group of lipids. And the first thing that she will want you to know is what is glycerol. So glycerol is this E-shaped molecule that has 3 alcohols on it. So this is glycerol. And triacylglycerol, I was right, has those alcohols replaced with fatty acids. So remember, fatty acid, oh my gosh, that's horrendous. That's a carbon right there. But a fatty acid is a carboxylic acid with a long tail. And so it's 3 fatty acids attached to that glycerol backbone, making it a triacylglycerol. And I can write that neater so you can have the spelling. This is an E. And does anyone have any questions about that? So this triacylglycerol is saturated. There are no double or triple bonds. But I could have a triacylglycerol that has kinks in it. So it's kind of like with the branching and how branching makes boiling point lower. If you have stuff that's disrupting these dispersion forces, it will make boiling point and melting point lower. Does anybody have any questions about that? You can kind of tell in space, these are like bouncing off of each other. This one points away. So they're not able to have as many dispersion forces. And these are also cis double bonds. So Dr. Creaky talked about triacylglycerols that have trans double bonds. And so what they decided to do, I need to somehow get rid of this, but I don't think I can. So I'm just going to cross it out. They wanted to make the unsaturated fats, such as vegetable oil and canola oil, that had that lower melting point, that lower boiling point. They wanted them to be able to be transferred more easily, like on ships. And so instead of carrying liquid that sloshes around, you can make it solid. And so they did this through hydrogenation, which saturated, right? It made the double bonds saturated. But what some of that did when they were being hydrogenated was create these trans double bonds. Now, what's different about these is if you remember with this, the cis double bonds push them all apart from each other. When it's a trans double bond, it lines up perfectly with how the rest of the molecule goes. And so this could actually have a higher boiling point and a higher melting point. And so because of this, because they are so different from the cis triacylglycerols, they cannot be processed by us. They cannot be processed by us within our digestive system. It gets in our arteries, it clogs our arteries, and that's what you hear about when people eat a lot of these trans fats. You may have heard about trans fats being bad, if you're a health science major. And this is why trans fats are bad, is because they cannot be processed. They have higher boiling points and higher melting points, and they get stuck in your arteries. Any questions about that? I know it's kind of a morbid way to end it, but all right. So that's the last thing that I have. I'm going to put up some practice problems, mostly the reactions. What I would say for the lipids is she may say, draw a saturated or unsaturated fatty acid, wax, or triacylglycerol. She may ask you to draw any of those. So just remember, saturated means no double bonds. Unsaturated means it does have double bonds. And then just to review what they look like again, because I'm not going to include them. Oops. Let me go back to this one. The fatty acid is just an acid with a long tail, and the waxes are an ester. Does anyone have any questions before I put up some practice problems? Oh my gosh. That's terrible. Sorry about that. Okay. I'm gonna draw benzene the worst way. I apologize. All right. So these are the practice problems. Realistically, there are, what is that? 7 of them, but split into basically 4 parts. So I'll wait around for a few minutes. Feel free to write them down. If not, if you don't have any questions, feel free to log off. Thank you for joining me. Again, I know it was a little bit weird, but I hope it was still effective, that you got to practice and look at some reactions and reiterate some of the stuff talked about in Kiki's lecture. So let me know if you have any questions. Again, I think you can privately message me too if you have a question, and I can go over them if you have any. So I'll stay on for a few minutes. But have a good night if you decide to leave.
Thank you.
Yep.
Have a good night.
You too.